right, so to recap the properties of polynomial functions, the end behavior x intercepts number of the turns or curvature changes and the maximum minimum values depending on the polynomial. I created this table, so go through the table. So the end behavior is based on if the leading coefficient is positive or negative, and that if the degree is even or odd. Okay, so that's very important, just so you have to remember that. And then the x-intercepts we have, so this is the x-intercept number of the zeros or x-intercepts. That's when the graph crosses the x-axis, and each one of them have a minimum and maximum depending on degree being odd or even. If it's odd, the maximum is n, so as even degree, the maximum will be n, but the minimum matters. Is 1 for odd degree, and for even degree the minimum is 0. Okay, so the minimum number of x-intercepts is set up for the odd and even degree. Maximum, they're both the same. And then here is the number of turns in the curvature or on the graph that you see. It's always 1 less than the degree of the polynomial in at most, because you could have less than that, but it's always the maximum number of the curvature change will be n minus 1. So I should say the maximum number in here, so make sure that you do realize that that's the maximum. Okay, maximum curvature change, because depending on some of the other terms in the polynomial, you may not get actually that many curvature changes. And then the maximum and minimum value of the function, and that is the part where the odd degree polynomial functions, they really don't have a maximum minimum. Remember, these guys only have the odd functions, these guys, they only have relative minimum and maximum. But the even degree, they do have it. So if it turns out that if a is positive, you will have a minimum value. If a, the leading coefficient, is negative, the graph is upside down. Therefore, you are going to have a maximum value of the function. All right, and that's basically it. I encourage you to play around with different functions and look at some of the behavior, write it out separately on a separate sheet of paper, analyze each of the graphs, and then the next section is to find the zeros of the polynomial functions. So before we go ahead with the x-intercepts, finding x-intercepts of the polynomial, let's do an example of looking at a question where we have to match polynomial functions with their graphs. Okay, we got 4 functions that are given to us, and then 4 graphs. We want to, based on the analysis that we have done, we want to basically create, we want to follow the pattern and therefore match the equation with the graph. All right, so first of all, type of the graph, we have noticed that based on the equations, so these are the equations that we have right here. These are the equations that we have. We have a quartic and the cubic function, and as well as a quintic power of 5. All right, so let's differentiate between the first the A equation and a D equation. They're both quartic function, but one has a negative leading coefficient. That means the end behavior of the graph matters now. So if it was, remember, because if it's the quartic function power of 4, that means that you should have in the graph, the end behavior should be in quadrant 2. That's the positive leading coefficient for the quartic function, but the other one should be in quadrant 3, and quadrant 4 is flipped over. So, and look at the possible curvature changes. So remember, they could have up to 3. N minus 1 is a number of curvature changes. So in this case, we can see B and D are the 2 possibilities here. So we have to figure out which is which. So notice that B is in the end behavior quadrant 1 and quadrant 2. We also can see possibly that the y-intercept which is this constant value here is always, this is the constant value, always your y-intercept are these two. These are your y-intercept, okay? So remember the constant term, these are the y-intercept right there, always. All right, D will be matching the graph B, so this is going to be D, okay, right there, the equation D, and equation A belongs to the graph D because it's upside down, and we can actually guesstimate that this part right here, that's your minus 12, and in here that is the minus 4. We can do that. Excellent. And then now our idea is to go and look at the graph A and C and match that. One is the cubic function, the other one the quantic function. So that's very easy to figure out now, because the cubic function, we can see that we have, this is the graph B, sorry, equation B. So look at the equation B and equation B and equation C we are looking at. All right, that's what we are looking at. So for equation B, that's x cubed plus x squared minus 3, and that looks like to me that, sorry, that's a plus 3, that's not a minus 3, that's a plus 3, just that, and that's minus 5x. Apologies. So it turns out that this is plus 3, so that means that that is 3 there. We do have only 2 intercepts, that's okay, and we can see that there is no minimum maximum in here, unlike the B and D graph. They do have a maximum minimum, right? So, and then the quantic function, the number of curvature changes should be 4. We got 1 here, 2, 3, and 4, right? So it turns out that this represents P of X, so that means that graph C is matching the equation C, and because of its, again, the end behavior is going from quadrant 2 to quadrant 4, that tells me that there is a negative in front. That means that it's been reflected over the x-axis. Excellent. So, and then obviously B, equation B belongs to graph A. All right, and that's how you analyze it. You just take it apart and you go one step at a time and then put them all together. All right, excellent. Make sure also that you are including, so graph B has a minimum, so that's the minimum value. We don't know what that is, that's okay. I mean, we can graphically see it. But graph D, that has a maximum value, okay? So that's the maximum value. We don't know what that value is, but it does. But the graph A and C, they do not have such maximum or minimum. They just don't have it. All right.